Okay, good evening, everyone. And this is week 8 of Essential of Data Science with our software and uh, sampling theory and linear regression analysis. I'm Kamna Mishra from School of Mathematical and Statistical Sciences, IIT Mandi. And this course is basically instructed by Professor Salab, who is from Department of Mathematics and Statistics, IIT Kanpur. Okay, so to begin with, we will start from the last class firstly. Uh, okay, okay, so these are some basic, these are some links you may need for this course. Okay, so main points for today's class are bootstrap methodology, we will discuss, then empirical distribution function, bootstrap biasness, standard error, and then we will see plugin principle. After that we will go through that how we can do all these things in our software, and after that we will see bootstrap confidence interval, how many methods are there to find the bootstrap confidence interval, and at that we will see what is the coefficient of variation. Okay, so in the last class, I have told you what is bootstrap methodology. So there is one point I have missed in that class. So rather than taking different samples from the population, what we are doing in the bootstrap methodology exactly, we are resampling, and that is why there is also it is uh, named as resampling method. So what we are doing is that we have a population. In that population, we are taking one sample with SRSWR. After that, what we are doing is that from that sample, which is of size n, we are taking n samples, and like a small n samples of size n, which is the size of original sample, with the help of without replacement. So what it will do is that in one sample of size 1 to up to n, it will resample it again and again and again. So in that 1 to up to n, so let me tell you how it will work. So let's say I have, uh, sorry. So let's say I have x1, x2 up to x10. Okay. Uh, this is let's say xn, so that it will be more generalized. So this one is, let's say, our original sample. So this one is original sample obtained from the population. Okay. The next bootstrap one. So we are taking B samples out of it. We are doing it B times. So let's say in the first one it is x2, x4, x1, x1, x3. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this one is, let's say, our B equal to 1. So it has resampled from this sample, and it has resampled it with size n. So this is size n for B equal to 1, for B equal to 2, let's say. So this one is, let's say, my x1, then x4, then x3, x4, x5, x6. So here 2, 4, 6, and then let's say x3, x2, x8, and then x1. So here it is b equal to 2. So similarly, b equal to b. So for these many times we are resampling this original sample. So this is the methodology given here, that take a sample of size n from n and it is original sample. Consider SR/SWR. Draw a sample of size n. So we have drawn a sample of size n out of it with SR/SWR from the original sample. So this one is named as original sample. Repeat the process and draw such B samples. Okay. So this is original sample and we have drawn these B original samples. Okay. Now after that, so this is how we have repeated B samples. Okay, hello Yogesh. So I
Good
was
evening. Good evening, please.
I was talking about the bootstrap methodology, and there is one point I have missed. I have understood. I have not understood it well, so I'm just saying it again. So what we are doing here is that we are taking a sample of size n from the whole population, capital N, and we are saying it is an original sample. So what I have said is that we are taking different n size samples from population n. So this is not we do in bootstrap methodology. However, that is one more way to understand the population, but right now here we are not doing in that way. So what we are doing is that we are taking a sample of size n from population n and we are saying it is an original sample. Okay. And then here we are using with replacement. So let's say I have a population of size n and I have taken a sample of size small n and I am saying it is an original sample. After that, I am saying draw a sample of size n with SRSWR from original sample and then repeat the process and draw such B samples. So what we are doing is that we have some original sample, one original sample of size small n. Then from that, using SRSWR, we are finding this B equal to 1, these samples. So uh, it can be like if I have, let's say, 1, 2, 3, 4, up to 10 values. So let's say this is original sample. Now from that original sample, if I will draw for b equal to 1 with using SRSWR, what will happen? I can take 2, 3, 4, 1, 1, 2, 8. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and then let's say. So this is our sample. This is our sample from this original sample. Got it? If I will say do for b equal to 2, so we can do it in this way. So this is what we are doing. We are considering our resampling method from SRSWR. So we can see that here also. So let's say, uh, sorry. So sample, I am saving it, let's say Z1, and it is 1 to 30, size is 20, replaces true. So now this Z1 is our original sample. Our population is 1 to 30 and our original sample Z1 here is this. Okay, this is of size 20 because I have given size 20 replaces true. Now what I will do is that I will take this Z1 2x sample Z1 size 20 replace true. So you can see that my population is Z1 now, and so this one Z1 is original sample. So this one is original sample, and then this one is sample generated for b equal to 1. So this is also of size 20, but it is coming from this. So you can see that if there is a number in between 1 to 30 which is not present in Z1, so let me just write unique Z1. So you can see that there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So there are 15 unique numbers. So as you can see that here 1 is not present, 2 is not present. So how how many times I will do sampling from this, 1 or 2 will not come in it because it is not present in the original sample. So this one is resampling. So this one is resampling, and we are doing it resampling b times. So is it understood?
Yes, ma'am, please.
So this is bootstrap methodology. So in that N we take this as original sample, and then we take B bootstrap uh, sample out of it. After that, what we do is that we evaluate the statistic theta for such bootstrap samples. Okay. And so there are b bootstrap samples, so there will be b estimates of theta. Okay, so from that we will find the statistical inference. Okay, so just for the theory, we have taken just 10, 20, 30. But in reality, if you want to use the bootstrap sampling, we generally take the number as 500,000, so that there will be a large enough number so that the resampling will give us our us some values which will be regarding to the real population. Okay, so this is what is bootstrap methodology.
Bootstrap sampling matlab means R, ma'am, na? R is the number of samples.
Uh, yeah,
That
you
is
can
bootstrap.
take R is the number of sample, B, like anything we are taking here B, you can take R.
Okay, okay.
Okay, so I'm just gonna repeat it real fast. So take a sample of size n, a small size n, as we always do, from capital N, which is the population, and we consider this particular sample as an original sample, and we do this with the help of without replacement methodology. And after that, with this sample, from this sample we are generating again and again samples of size n, and we repeat the process and draw such b samples. So as I have said that here the population you can see is 1 to 30 is Z1. So Z1 is, I have taken original sample only one time from the population. After that, you cannot see 1 to 30 anywhere. So after that, I have not done this. But after that, what I will do is that I will resample B times. So this one is sample which is taking from the original sample, and this is of size 20 because the Z1 initially is of size 20. So I'm taking sample 20. So this one is B1. So if I will run it one time, this one is B1. Let me just remove all these things. So if I will just run it, it is B1. it is b equal to 2, it is b equal to 3, it is b equal to 4. So somehow we are generating our samples b times, so it is at b equal to 1, 2, 3, 4, up to b times. So this is how we are generating the samples. And for each, we will find the mean or variance or standard deviation or whatever estimates we want from that. Because the thing is, if you do not, uh, if you have a data which fits a distribution, so if it will fit a distribution, we know the mean of distribution. We will just say that, okay, this is the mean, this is the standard deviation. If you don't know the distribution of a data, then we can do the bootstrap, we can do the enough sampling, and with that sampling we can find its mean or whatever estimates. Another thing is that sometimes we have the distribution, but finding its mean is very tough. So, like in the calculation, you cannot calculate that integration, or you can calculate even I have one paper and what I am working. So it is very tough to find that expectation only. So for finding the variance, it becomes more complex. So that is where we can use this kind of methods. Okay. The next is that EDF. So it is empirical distribution function. So it is same as the not actually same, but it is similar as the cumulative distribution function. I think if you try to remember that you have seen this empirical density if you when we do the chi-square testing. So in my BSc, I think I have done that. So what we have done is that empirical distribution gives the equal probability to all the values. uh, so empirical distribution function. So empirical distribution function is basically when we do such kind of like uh, tossing a tossing a coin and a die, etc. So it will, like, the probability of coming one is 1 by 6, and then for all it is 1 by 6. So that is how we define the empirical distribution function, that how many times it is coming and then dividing by the whole. So if we have some data and we cannot find and we cannot define its cumulative distribution function, and we do not have the information regarding that, then we use this concept of empirical distribution function. And also when the size becomes larger, it will say that the cumulative distribution function will be equal to the empirical one. Because understand it in this way, that the cumulative one is like theoretical and the empirical one is like we are taking all the information from the sample. So what we say is that the probability of when we are tossing a die, the probability of coming one is 1 by 6. So we say that if we toss a die enough number of times, so enough number of times means 1,000, 2,000, 10,000, or lakh. So we say when n goes to infinity, it is saying that from the sample also its probability will come near by 1 upon 6. So that is how we say that whatever is happening in the reality will match to the theoretical one. So for the large sample size, the cumulative distribution function will be similar to the empirical distribution function. So if you do not have the information regarding the probability distribution of a data, then we try to find it with the help of empirical distribution function. Okay, so EDF is basically, so if I have x1, x2 up to xn, it assigns probability 1 by n to each. Okay. So, if you will toss or roll a die 100 times, so if you will roll a die 100 times, so if it so the possible outcomes are 1, 2, 3, 4, 5, 6. So if xi is equal to k, so its probability will be, sorry, if let's say this is the nth time it has came. So if let's say if one is coming 20, sorry, 10, 20, 12, 20, 10, 18, 16, 24. So its probability will be 0.12, 0.20, 0.1, 0.18, 0.16, and 0.24 for 1, 2, 3, 4, 5, 6. So this is how so this is EDF. Now this has been rolled for 100 times. So if we will roll it for 1000 times, it will change. So after that it will be near to 1 by 6. So this is the reason why we do that. Okay. Uh, Now, the thing is that it can be proved that the F bar, which is F1 cap, so these are basically estimates. So these frequencies are basically estimate. So this is a sufficient statistic for true distribution. Okay. So, sufficient means whatever information we have contained in that x1, x2, that will be contained in that f cap. So, if I am saying that uh, whatever information, so whatever information this means, whatever information these samples have. So, this particular one, this one will have all the informations, like it contains all the information. So how we can say that? So if I have b samples, if it's mean, let's say if it is mean, uh, is let's say for the first one it is 10, for the second one it is 10.3 or something like that, then we know how the sampling is done, and then we can find the variance. So we can see that whether the numbers are taken in the sample from very far. If variance is high, so it is far, and if variance is low, so numbers are very close. So that is how we can say that all the informations are in this particular statistic. Okay. The next one is plugin principle. So the plugin principle is okay, so plugin principle is a simple method. So what we do is that we do the estimation of parameter based on empirical distribution function of whatever we have discussed here. So theta is our parameter. Then we do it with TF. Okay. So we estimate this function, and then of the probability distribution f, the same function, and we say that the estimates this also will be equal to t f cap. So these are the estimates. So the next thing we will go through, because there are a lot of basics also in that. So if the estimator, as I have said, in the time of, if you want to take the mean, then we can find the mean in that terms. And If you want to do the variance, then we can find variance in that way. And this is how we can find the estimators also. So if you have the population, I think I have said it, so this is just written again in the similar way, so I'm not discussing it again. Okay, the next uh, okay, so the next point is that we can find that standard error. So standard error can be found by the standard error of this theta cap. So this is the parameter basically. So this is under root VB, and then VB can be found in the similar way we have found the variances till now. So I will just write that the theta cap uh, will be 1 upon B summation B equal to 1 to B theta cap x b, and then vb will be 1 upon b minus 1, because this is how we take like the sample variance, and it will be also be equal to 1 to capital B, and then theta bar xp uh, minus theta no theta cap whole square. Okay, so we are using theta naught so that it will be uh, in the terms when we will see the bootstrap. So in the R, we can see that it gives the real parameter with this theta cap, the original one. So this is why we are writing in this way. Okay, so this is the mean, this is the variance, this is the standard deviation, and this is the biasness of B, which is theta bar minus TF cap. So once we do it in our software, it gives us all. So it gives us what is the original value, what is the standard error, and what is the biasness. So these are the parameters the bootstrap methodology in the R software gives us. Okay, the next is the coefficient of variation. So coefficient of variation. So how so coefficient of variation is very simple. It is CV is given by sigma upon mu. So uh, it just says that uh, let's say my sigma is 1.10 and 1.2 and mu is 10, and here my sigma is 3.4 and my mean is 10. So you can see that it is 0.12 and it is 0.34. So coefficient of variation, you can see that mean is constant in both, so variation is high here. So that is what we say is that if mean is same but the variability is high, so we say that coefficient of variation is high. But that what we can say when the mean is same, right? So uh, till now we have seen that when the variability is high, so we say that we want to minimize the variability. But what if the mean is also changing? So I'm saying that 1 by 2.10 and 3.4 by 20. Now if I will just give you the variability, you will say that the variability is high in the second one. But what about mean? What if the mean is also high? So coefficient of variation depends on two. So if you will see the coefficient of variation, you can see that how much it is variating from the mean. exactly. So this is why it can be useful here. Okay, so this is one thing. The next is that we will do all these things in our software. So I have already installed the package. So library boot and library bootstrap I'm using. So you need to install the package firstly boot, and after that you need to install the package bootstrap later. So firstly we need to only install the package boot and then take the library boot. Sorry. Okay, so this one is the library you need to take. Okay, so after that we will see here. Okay, so boot is already open. So here you can see that data. So data as a vector, matrix or data frame is, if it is matrix or data frame, each row is considered as one multivariate observation. Okay. Okay. The next is statistics. So a function which was applied to data return a vector A of is the statistics of interest when sim is equal to parametric. The first argument this must be a data. For each replicate simulated by a data returned by ren.gen will be passed. Here you can see that for in all other cases statistics must be at least two arguments. Okay, so let's say we want to find the correlation between happening between two things. So we need to give the two uh, uh, what to say the a vector of two, a data frame of two columns. So can you give me some real life example where two things are correlated and we can find that how much it is correlated or something like that, that one depends on other, and then we can make some data out of it. Any two things, like on which we can make our data. Like the sir has given that if a student,
Yes, yeah. Marks and hours
yeah,
of study.
so not that, that is something sir has given, so you need to give some different example. Like, can you think of something different? Like, there are a lot of things which will depend on each other, right? Yes, so what can be, what can it be?
Uh, we can go for cricket match. So number
Okay,
of players and runs made
runs will depend on what?
uh, depend on the number of balls they batted.
uh yeah, okay, so let's say uh
Yeah, number of balls they played
okay,
and number of
so
runs scored.
okay, so let's say I'm writing here. So this one is cricketer number. Uh, so let's say this one is cricketer number. This one is the number of balls he played, and this one is runs he made. Okay. So uh, cricketers, let's say for both side we are taking. So I think we can take
1 to 22. 1 to 20.
if 22. I think if the 10th one is out, we cannot
Yes.
let the 11 play. Okay, so 20, up to 20 we are taking.
20, yeah. Okay.
So balls can be I don't know, I'm just writing it somewhere. So let's say it is 7, 4, 9, 10. Okay, so we need to write, so we can write directly data there. So let's say I am saying that, okay, the cricketer. So I'm
Cricket
saying, so
CT is equal to 1 is to 20.
okay, and then we can say that the balls. So I'm writing a number of balls as C, and then we can take 9, 10, 12, 7, 8, and then 19, 13, 2, 14. Now again.
1, 2, 3, 4, 5, 6, 7, 8, 9,
Okay,
10.
so it is 10, and then we need some more. So let's say 8, 10, and need 1, 11, and then 16, 6, and then 20. Okay, how is that? 17, and then
20.
we take 11, let's say 9, and 12. Okay, so this is 20. So this is number of balls they have played, and then number of runs they have made. Okay, so in 9 balls, so maximum they can make 9 times 6. So the minimum I'm taking for 6 times 6 is 36. So they can
Minimum
make,
is 6, so 36 will be the maximum. So we'll
and
take
here is
36.
2. So 2 में कम होगा, बाकी सब में ज़्यादा होगा. Okay,
Yes, yes.
so let's say for the ninth one I'm taking as 18, and then 23, and then for the 12th one, um, say 20. Yeah, so 19.
15. Okay, we can take 19, 20, 15, 13, 18, 38.
Okay, one, 2, 3, 4, 5, 6, 7. No, 2, 4, 6, 7. So for the eighth one, I need to take less. So 2, 4, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so for the eighth one, so let me take just uh 6. Okay, and then it will be 16, 19, 31, 22, 26. Okay,
Nine, 18, 10, 23, 12, 27, 19,
okay.
8.
So all are 20.
Yes, one
So
by
this
one.
is number of runs, number of balls. So we have made here two, this NB and NR. So we are saying that these can be dependent on each other, and with the help of Bootstrap, we will see how dependent they are. Like on our own, we are saying that they are dependent, but we can see how they are dependent or not. Okay. Uh, So here are some things which are given. So R is number of bootstrap replicates. The simulation can be ordinary simulation, the parametric, balance, permutation. There are a lot of. And then what is S type? So I is indices default, F is frequency, weights, and then strata. So whether we want to use the strata or not, so we have discussed strata before. Then there are a lot of things, so depending on what you want to do, we can take those things. So here we are using just simple bootstrap, so we will just simply run for this particular one. Okay, so what we do is that firstly we make a data frame.
Data
So okay, so I'm making the data frame as ct, nb, and r.
and B and R is equal to data frame, data dot frame,
And then data frame will
and
contain the ct, nb, and nr. So it is a v.
CT and B and R.
So this is our data frame, that these are the cricketer, this is the number of balls, and these are the number of runs it has made. Okay. Uh, Now we will make just one function, and okay, so this one will be number of, and we are doing it to find the correlation. Sorry, function we are defining as d comma I, and the function is taking uh, d2 as d, and this return the correlation of uh,
D2 and
so it will be for np, sorry, correlation will be in between uh, nb and nr, right? So we have made this function. So now we will do is that core.
ma'am, could you just tell this how we are relating this correlation? So
Uh,
NBN is
we want to find the correlation between these. Okay. So
balls and runs.
yes. So to find the correlation, we are using this NB and R. If I will do this, uh, return. Uh, okay. So here I have written D2. So let me just take C, D, N, B, and R, and here N, B, X. So here is our real correlation, and with the help of bootstrap we will find that how we can find the bootstrap one. So here it is saying that it has the correlation of 0.5460917. So here it is for whole population, then we can do the samples, etc. So when we So this is our real value. We will see how the core boot will perform. So I'm just writing the core boot because it is for correlation. So bootstrap will be data will be coming from this data, which is CT, NB, NR, and the uh, statistic is NB and R is equal to 500. Could not find the function boot. Oh, I have taken the library boot. Okay, just a minute and I will explain everything. Okay, so this is core boot, this is original one, this is this one. Okay, so what we had done here is that we have firstly, or let us do this before this. Okay, we have what we have done here is that firstly we have taken the data. Then we have found its correlation. What is the real correlation? And to do the bootstrap, now how the bootstrap will find the correlation, right? So for the numbers, we know that if it I will give it a function just core ctnb this, then it will give me the correlation. But here, how it will find the correlation? So for that, I need to give it a statistic. So I have given it a statistic that when you have this uh, D I, so I will be like 1, 2, 3 up to 500 because I am taking here as 500. So it will take up to 500 and then it will take the correlation of this NB and NR. So data I have given. Okay, let me just copy this, what it is doing. Okay, so here, maybe, okay, this is space. So when I have the data of this data, so I can just find the correlation of uh, CTNBNR $1 NB and then CTNBNR $NR, because this is the second column, this is the third column, this contains the number of pause, this contains the number of runs. Now inside it, what I have given? I have given the data, which is CT, NB, NR. Statistics as this, R is this. So statistics is NB, NR. What it will do is that, what this function will do for R equal to 1. So what it will do? R equal to 1. So bootstrap, we have this many samples. So for R equal to 1, it will take samples from that. Got it? From CT,
Yeah.
NB, NR, it will take, so 20, we have N equal to 20, so it will take 20 samples, right? Now in that 20 sample, what will happen? It may take cricketer 1, 2, 13, 13 again. So it can be 9, 10, 7, 8, 13, and then again 7. So it can take on its own. Okay, and in the same will be taken for the NR. So it has taken this one sample, and for that it has created its CT, NB, NR. For that CT, NB, NR, what I am saying is that find, so it is D, okay, and then I, so I for I equal to 1. Now this Di is saved. So what I am saying, Di is saved in D2. So what I am saying is that return me the correlation of this D2, NB, and NR. So now this one is our D2 for the first sample. So this one is, let's say, D2 1, or sorry, this sample is, let's say, D1 comma. Okay. So D1 comma is CT, NB, NR. So it will return me the correlation for this sample for the first one. Now it will take again resample from this original data. So for R equal to 2, it will do the same. Take 20 sample. It will be D2 comma this. Again, it will find the correlation between all these values, and then it will return me again one correlation. So it will do it 500 times. Now I can take it 1000 times also. So here, now you can say that what is the biasness. So biasness is that uh, the original one is this, the biased one is this. So biasness is from the real value, how much biased is the is these bootstrap samples. So this is our real value 0.546, and this is the biasness, which you can see is very small. So it is 0.0224. So you can see that original one, and biasness is what? Mean, and then a little bit biasness from that, and standard error also you can see is very small. So variation is also very small. So this one is correlation. Yes.
So I mean the actual that
Hmm.
bootstrap statistics will be original one.
Yes, this one is original, and this one shows you how much it is biased. So
Okay.
original one you can see here I have found. Here you can see this is the same. The correlation between the real one is same whatever is given here in the original one, and the biasness it has after finding its mean, this one is the biasness and this one is the standard error.
Standard.
So this is how much it is biased from the real value. Okay. uh, so this is bootstrap. Now, uh, if I will try to find the summary of this. Okay, so summary say that T naught is one numeric T. So T naught is our original one, which is one. So T naught is basically the real correlation, right? So the real original correlation was 0.546017. So it has length 1 and it is numeric. The T, so T we have generated. So here I have generated 1000 times. So it is of 1000. So it has taken the seed. So seed it has taken Y, because if I will do, let's say, this again. So it is changed. So biasness is changed. Standard error is also changed. So it has taken the seed inside of it. Statistic is one statistics, which is function simulation one, and there are S type. So S type you can see from here, which is one, and then the strata, and then the weights. So strata and weights, these are strata. So we have not divided it into a small sample. So strata is basically the full one. So we have taken sample of n. So n is 20. So strata is of size 20. So it has just one. Okay. So this is the summary of this correlation one. So now, uh, if I will do the mean, okay. So correlate T. So you can find that these are the correlation it has found with using its samples, which has it has created. Okay. So the first sample it has created, its mean is 0.53, next one point 0.5, then zero point 0.6, and then you can see it is 0.07. So it is very different. But when you take for overall 1,000, it will be uh, better. So biasness for overall is less. So for sometimes it is very less, sometimes you can see it is very high, it is 0.79, sometimes it is more high, 0.86, 0.87, and 0.88, and sometimes it is very low, which is 0.24, or here 0.00867, so almost no correlation. So it has taken these, so the samples it has taken, this is the correlation of these. Okay. So if I will take mean of it, you can say this is 0.53 this, and if I will do minus oh sorry, just core put, and then T naught. So T naught one is the original one. So this one will give you the biasedness. So if I will just run core boot, you can see that this one is the original, this corpus T are generated bootstrap sample. So if I will minus the mean of bootstrap samples minus the real one, we can find the biasness. So you can find this is the biasness, and the standard deviation is standard deviation in these samples. So you can see that standard error is found in these samples. So this is how you can understand. Now, if you will take core boot and here. So here you can find all these things. So what is the data? So data I have given, T naught, T, and then R, etc. So here you can see what are other things. Okay. Okay, so we have executed this, and the next is bootstrap confidence interval. So, whatever we have done till now, we have always found the coefficient confidence of interval, because just by one point we may not understand it very well, that how the samples is going on uh, inside of it. So we find what is the uh, confidence interval. Now, the general way we do is that we take, when the sample variance is known, we take the z. When the sample variance is not known, we take the t in to find the confidence interval, if you may recall the previous classes. Okay, so here there are five methods. There are not just two methods, there are five methods. So bootstrap confidence intervals. So there are five methods. So basically, confidence interval is, right now, if you have the correlation, if you have mean, this one is just 1 point. But what if it is lying in between something, right? So if I'm saying that, let's say my correlation is zero point 0.6, and somebody is saying their correlation is in between zero point 0.5 to zero point 0.7, however my correlation is in between zero point 0.3 to zero point 0.9. What will happen? uh, their data is more reliable rather than mine, because if my data some point the correlation is very low, then it may be not depending actually, or if sometimes it is so high, then it is depending so high. So I need to have the better methodologies for this. So it is very important to find this statistic also. So for that, we will see what are the methods. Uh, okay, so okay, so now there are five methods. First one is percentile method. The next one is normal distribution. After that, D distribution. Basic confidence in, and the
Percentile, normal, T, and BC.
and the next one is bias corrected.
Related, excellent. That is
Accelerated. Okay, so confidence interval. I'm just writing. Okay, so percentile method, normal distribution, T, basic confidence, and the bias corrector. Okay, so first three I think are very just name dependent. So percentile method is basically what you divide. You have a data. So in that data, what we can do is that we can make the histogram of it. So I can make histogram of it. I can make histo of core boot. Sorry, not core boot of T. Right. So you can see that this is the histogram. Now, in between, so minus zero point 0.5 is very less. It is just, I think, one number. So you can see that histogram is maximum at this place. In the real one, it is 0.546. So it is something here. So something here it is maximum. So you can see it is maximum here. Now the percentile method does what? So since B is very large number, so percentile basically means like if you have quantile, you divide in four parts. So percentile we divide in that part like 100, uh, and then you can see that you just remove this 5 and then the last 5. So if it depends how many, for how many you want to do. So here I have taken B is equal to 1000. Okay, so for the percentile one, so since B is equal to 1000, or let's say R, so that it will not take increase the confusion between our software here. So R is 1000. Okay. So for the percentile, if we want uh with the, let's, so the we say the confidence interval. So if we are taking as uh zero point 0.5, so zero point 0.5 or 0.25. So if I will take alpha as zero point 0.5, which is in general, so 95% confidence interval. Okay, so from the left and from the right we take, so alpha by 2 is 0.25 for both the sides, alpha by 2 0.25 0.25. So uh, here it is 0.25 and here it will be 0.975. So our uh, numbers is 1000. So what we do is that based on percentile we take 25 here and 975 here. So this is just percentile. So we firstly take this theta 1 star, and then So we are take sorting basically. So sorting needs, because otherwise we cannot make it in this way. Here also you can see that data is sorted, right? That is why it has firstly minus 0.05, then what is in between 0 to 0.1, then 0.1 to 0.2, and then 0.2 to 0.3. So data is sorted here also. So once you have the data sorted, to find the 95% confidence interval, we will have theta cap star 25 to theta cap star 975. So now this is nothing but our confidence interval. Okay. So this is our 95% confidence interval. Okay. So this one is based on percentile method. Uh, okay. The next one is that we can use, now this one is 95 percentile. You can take 99 percentile, you can take the 90 percentile according to your work. Okay. The next is based on, so this one is the first one. The next is normal distribution. The next is normal distribution. So approach to consider here, in the normal distribution, if you may remember, I have done this here somewhere. Okay. Not in this class. In this class. Okay. So not here. Okay. In stratified samples also, I think we have done that. This is NI variance, proportion, allocation. Okay, here. So confidence interval is like always same how in the normal one. So this one is the uh, theta cap minus the real theta divided by the variance of it, sorry, standard deviation of it. So here also we will have this theta cap found from this xr star I'm writing minus the real theta divided by under root of VR. Okay. So this is a standard deviation. So this is this we say that this will follow the normal 0 1. So to find the confidence interval from here, what we do is that we say it is in between minus z alpha by 2 to z alpha by 2, and from here we can see our uh, theta naught cap minus z alpha by 2 under root vp 2 theta cap plus z alpha by 2 under root of vp. So this one is our confidence interval with using the uh, normal distribution. Now the similar one is for the t distribution also. Uh, so for that we need to have this just bootstrap. So uh, bootstrap statistic, whatever we have bootstrap statistics. uh, so I'm writing in the same way. All it is that rather than this, it will follow the t distribution with the degree n minus 1. Okay. Okay. So I am writing, it will be just theta cap minus t alpha by 2 at that u. So under root vb comma theta cap x bar statistic minus, sorry, this one will be plus t alpha by 2 u under root of vb. So this one is our, just replace this z alpha by 2 by t alpha by 2, and in the z there is nothing like degree of freedom, so here only we use degree of freedom, so a u will come. So according to the degree of freedom we will take this u. Okay. The next one is, this one is second, this one is third, now fourth. So the fourth one is basic confidence interval. So here the proof is not given, it has just said that 101 minus alpha percentile confidence interval. So 101 minus alpha, now alpha is, if it is zero point 0.5 or 0.25 based on that. So it is 2 t naught. So t naught is the real one minus tau 1 minus alpha by 2 comma 2 t naught minus tau alpha by 2. So this tau alpha is a percentile of distribution of bootstrap. Okay. The next one is bias corrected accelerated CI. Okay. Uh, so this is given by, so this is bias corrected percentile. So this is what we say is that we do not divide it into 1 minus alpha and alpha by 2. So we do not divide it into like alpha by 2 from the both side. So we take it in this way. Uh, it depends on this accelerated parameter. So here it can be given by the theta cap a1 comma theta cap a2, and a1 a2 are these bias correctors. So this is phi of z naught cap plus z naught cap plus z alpha divided by 1 minus alpha cap z naught cap plus z alpha. So z alpha, you know, z alpha, like it is for normal distribution. This phi, this is the CTF. So these phi is CTF of normal 0 1. So this one is A1, and for the A2 just replace the alpha with 1 minus alpha. So it is z naught cap plus z naught cap plus z 1 minus alpha divided by 1 minus alpha cap. Uh, yes, z naught cap plus z 1 minus alpha. Okay. So these are some five method of bias corrected. Uh, okay. So now the choice between the confidence intervals. So we say is that when we have uh, our distribution which is symmetric, which is bell shaped, then we can use any percentile method or t. When it is not symmetric, then we use uh, bell percentile method. Now why is that? So the normal distribution, as we know, is that it works, it is the symmetric distribution. So if uh, it is symmetric, then it is good to find the normal one, confidence interval with normal one, otherwise not. Now there are some cautions for this bootstrap confidence interval. So basically this is not for just for confidence interval, this is for bootstrap samples. So firstly, that the sample size need, if the sample size is very small, the bootstrap will not work fine. Because you can see that if when in the time of t, when we have seen this t, so if I will take just starting samples, there was a time when the correlation was in minus, or let's say it is 0.003, but the real correlation is zero point 0.5. So if you will have 10 samples, and for some it is zero point 0.6, but for some it is 0.05, so it will make a very major difference in the real one. The next is that bootstrap doesn't give the reliable results when it has infinite second movements. Now infinite second movements means infinite second means is expectation of x square. So if you have infinite second movements, that means the variability will also be infinite. So if you have the infinite variability, so if the variability of anything is very high, then we do not know that whether it is close to the mean or not. Okay. uh, it is not reliable when finding the extreme value. So if you want to find the bootstrap, if you want to find the correlation, it is fine. If you want to find the mean, it is fine. But if you want to find the extreme points, then the bootstrap may not work, because it may take the middle values or the lower values, then the extreme ones may not work. Okay. So it works obviously well when it is symmetric, smooth. So firstly, we need to take this. Okay. Now the approach is that we need to train our model on the sample, and we evaluate the skill on the model which are not included in the samples. So what we do is that basically if I have a uh, let's say of 1000 values, I will train my model for 900 values, and I will check my model on the remaining 100 values. So that is how, like, whatever way any method will work, we can work with this also. Okay, so at, after that we will see how we can find the these things in our software. Okay, so core boot we have already. uh, Now if I will, okay, so the core boot plot will give you much more information rather than just histogram of it. So you can see that just increase it. Okay, so you can see that it is zero point 0.5, it is the line at this is saying what is the original one. So you can see how it is closer, but it is uh, more here also. So you can see the biasness in the positive one. Okay, now here if you will see that, you can see for most of the part, just from for if you will just remove the uh, extreme points, mostly is following the normal distribution. This line shows that whether it is, so this is quite quintile plot, QQ plot we say. So if it is in, most of the points are in this line, so you can see out of 1,000 maybe the hundreds are here and here, but mostly are in this. So we say that it is safe to work with the normal distribution. Here you can also, you can see that it is, if you remove just some outliers, so you can see from here, sorry, from here to here, from here to here, it is almost the normal distribution. If you see just from here, this point, you can remove just some 50 to 60 points. Okay, so we can try the confidence interval of normal distribution also. Now for that, we will use boot.ci. So boot.ci. Okay, so boot.out is our core boot, and if I will just give index equal to 1. Okay, so firstly let me show you here boot.ci. Okay, so it says that if index is 1, so if you will rather than index 1, you can write this type. So if I will write uh, type equal to C norm, so it will give me only normal. So if I will take norm comma sorry, so it doesn't give for the T. So if I will do norm comma basic, so it will give me the normal one and the basic one. But if you do not write, if you do not want to write all the names again and again, so all you need to do is that write index equal to 1. So index equal to 1, it has given for the normal one, you can see uh, it has given for the basic one, it has given for the percentile, it has given for the bias corrected, but it has not given for the T, and there is a warning message that bootstrap variances needed for the studentized intervals. So we know that for the T distribution, we need to have the variances. If there is no, if, but here we have not given the variances of it, so that is why we cannot find the intervals for the by using the T distribution, right? So here we have for the normal one, for the basic, for the percentile, and for the bias corrected. Okay. Okay. So now for uh, the bootstrap, for the T, we need to install that this package like bootstrap, and then I have already installed. So I have just written the library bootstrap. So here it will be boot T. Okay. Sorry. Okay, this is library bootstrap. Okay, so here you have both T. So you need to install for a library for finding for the T. Okay, so here you can see now X, which is your vector. The theta is function to be bootstrapped, and then SD fun. So what is the standard deviation mean, so you can see from here. So the next is number of bootstrap HD, number of boot T, and then there are a lot of things, and then percent. So as I have said in alpha, so here you can see it has given for 95 percentile, so we can take that whether we want the percentile different, so 95, 99, 97, point 5. So based on that it can find. Okay. uh, so what we do here is that, so uh, here. Okay. So 1 to n is 20. We have 20. 1 to n. Theta is core boot x theta. Okay. So in the core boot, okay. So what we have done is that, okay, let's see. So theta we have is CT, NB, and R. Okay. And unused argument. Okay. There is some error. So function, in the function I have given this NBNR, which is given as function. Okay. So what we can do is that we can define NBNR1 x comma. So here I'm just writing directly that you find x data x1 comma x data x2. Okay. So I have defined this correlation again. Uh, so NBNR1. So in boot.ci we have given the core boot, and based on that we want to find its percentile. But here, because we need to calculate the variance etc., which is not present in the core boot, so we need to take that sample again, and then we need to give n pot directly, so we can give it 1000 as we have done before. So here you can see its percentile. So it is 0.001, 0.01, 0.25. So if you want the percentile from 95 percentile, so it will be point 0.025 to 0.0524. So we can give here the percentile. So if I will give the percentile as C, comma, 0.025, 0.975. So it has given me this. So you can see that here it is 0.25 was different, here 0.975 was different. Whereas if you will do this, you can see that confidence interval in these two are same. The normal is one is 0.1085, 1.1019. So it does not matter how many times I will run it, it will be same. But here it is changing. You can see just one, and then here you can see it is changing. Why? Because it is taking from the starting. Here I have given its is core boot. So the samples are already came. Now does not matter how many times I will run it. There is one sample, so it will find the confidence interval same again and again. But here you can see I have given it the function correlation and the data. So it is finding its correlation, it is finding its variance which is needed for the t distribution. So that is why it is needed to create the samples again and again. So it is creating the sample again and again, and that is why its confidence interval is also changing. Okay. So this is the difference between the uh, all the other methods and this one. Okay. Now the next one is that uh, the next one is coefficient of variation. So we have found our mean, we have found the biasness, we have found the standard deviation, we have found the confidence interval. The next one is what? The next one is the coefficient of variation. So now the coefficient of variation is sigma upon mu. So if I will take square root of uh, okay, so student marks okay, so marks CV. So if I will do run CV and I will make a function out of it similar way, just di, and what we do is that we take this and we return. So here we are finding the coefficient of variation only on runs. So how runs are variating, because the marks sorry, so the number of balls, so variation on number of balls does not matter, how many runs are made that matters. So we are making this on uh, runs. So it is square root of variation of this G2 NR divided by the mean of D2 NR. Right. So now if I will do CV boot and I take boot data as our data CT, NB, NR, and here I have a statistic as run CV and R is equal to, let's say, 1000. So now CV boot is created. So you can see that original one is this, biasness is this, the standard error is this. If I will take the real one just for the clarification, just for the verification, so we can see that CT and B and R and then divided by mean of CT and B and R. So you can see this one is the original one. So this one is the original coefficient of variation for runs. This one is the biasness and this one is the standard error. Right. So this one is the coefficient of variation. If we will try to find the summary of CV, so we can find the same summary, we have the same strata and etc. So now the mean of CV T, so this is 0.331276. uh, if I will try to plot this, so you can see this is also following the normal distribution. So this one is uh, coefficient of variation. Now with this coefficient of variation also we can find the uh, confidence interval of this coefficient of variation. So we can write, sorry, put dot out is equal to CV put, and I'm writing just index equal to 1 so that I can have for all. So you can see that these are the intervals for uh, this CI. Okay.
Index is one that has been man. Index one.
Uh, if you so what you can do is that if you will, if you want the confidence interval for with the help of normal, basic, etc., then you can write the type. If you want for all, so normal, basic, percentile, and biased corrected, and it does not work for the T distribution. So you just need to write index equal to 1. So it will cover for all.
Okay.
Okay. So this one is up to the lectures we needed to cover. So now we will do some just very basic questions. So just to remember all these things. Okay. So first one is very basic. So in a bootstrap analysis using uh, the bootstrap one, uh, sampling, what is the, if it indicates the samples of 1,000 resamples, then what is the number of bootstrap sample?
1,000.
1,000. Okay, so nothing to thought of. Now here, so how you can find uh, which command returns the mean of bootstrap replicates?
Replicates.
Bootstrap samples, whatever we have, how we can find the mean of it?
Mean that boot results.
Okay, so
Dollar T.
yes.
Dollar T.
Yes,
No.
yes, dollar T. So the T one will save this. So here you can see I have used dollar T. Uh, the next one is the observed statistic in bootstrap output. So what does bootstrap result at dollar T naught?
T naught is the mean of boot original sample. No.
Yes, this one is original statistic. Observed statistic from original sample. This one.
55 and what result 20 equals 50.0. What is asking mean
What is
boot
biasness? So biasness
is
is
minus
that,
no? So
yes.
5.3.
Okay, so
That
you need to remember that we need to minus this one minus this. So it will be 5.3.
yes.
The next one is that computing the bootstrap standard error. How do we calculate the bootstrap standard error?
Standard error was as the
Yes.
boot result dot dollar T. No. Yeah.
Yes. The next one is the percentile method for constructing a bootstrap confidence interval is based on.
Quantity distribution, the empirical percentile method based on the standard normal distribution. No. Quantities of T distribution. Bootstrap replicates, no? No, I think
Yes. Yes.
bootstrap
So for the percentile, basically, empirical quantiles of bootstrap replicates. So
bootstrap replicates.
you divide in that part. Okay. The next one is this interval adjust for. So that I have not said. So I will just say that bias corrected and accelerated that confidence interval adjusts for both biasness and skewness. Okay.
Okay.
The next one is that consider a 95% bootstrap confidence interval obtained from an analysis. Which method yields the shortest interval?
So test man 45, 85, that is 40. 48, 82 is 34. 47 and 83, that is 30, 33 plus 36. BCMM 30.
Yes. So PCA will be the shortest one, but it is not going to happen always. So it is happening is in this particular case. Okay. Now the T method bootstrap confidence interval, the fifth percentile of bootstrap distribution is reported as minus uh, 210. Then what does this value indicate?
Or below 5% of the estimates are below 201 estimates are above. This was, what was that, 5%? What will be the answer? Well, bootstrap confidence interval is 5%, right?
Okay, so if you have a distribution, let's say जो भी है, if you have fifth percentile value given, that means that the 5% values are
Or
below
below,
this.
below 210.
So this will be below
Yeah,
this. Uh, the next is uh, in a T method,
I think.
bootstrap analysis, the median of both star replicates is reported as 25.8. What does this represent?
A T method bootstrap median.
So median. What does median shows?
Median mean half of the values are no, that is mean.
Yes. So median means 50th percentile.
50th percentile. Yeah. The 50th percentile value of the bootstrap replicates.
Okay. And next is if 99 percentile of bootstrap distribution is 100.5 and if 97th percentile is 90, what is the difference between these percentiles? This is just minus. So 100.
Minus, yeah.
So it is 10.5. No?
Okay.
Okay. Now a T method bootstrap is 99% this. What is the width of this interval? So width is simple. So it is 5, 5, 10, and 7 to 9. So it is no. Oh, 75. Sorry. So
Seventy-five minus
it is 5, not this. So
325.
5,
Also
yes.
70.
So it is 325.
Okay.
The next is if the mean of bootstrap replicates uh, is 60.2 and the observed statistics is 65, then what is the bootstrap biased? Yes.
60 and the observed status 65. What is the bias? 4.2. Bootstrap replicate 60.2. Statistics is 65. 60 minus that is 65. No, minus 4.8. That's
Yes.
bias minus 4.8.
And indicating underestimation or indicating overestimation. So it is underestimation because it is less.
Okay.
Because the real value is 65, it is estimating 60.2, so it is underestimating something, right?
Okay.
The next is assuming the bootstrap output is stored in boot out, which command correctly computes standard error. So we have done this before, so same question.
SD boards, yeah.
The next one is that what is which function is boot package is used to compute the bootstrap confidence interval, and which method does it support?
But boot CI, no?
And what does it
CI
support?
supports normal, basic, percentile, BCM. All four, man. Boot CI.
Yes. So it supports all four. Okay, so these are some questions regarding to this class just as a revision. Okay, if you have any question you can ask.
And when the audio is loaded, this file, the sound quality is very poor. Last video file which was
Okay.
added, so the your speech was very faint. It was so
Okay.
when I reviewed it once while solving one of the assignment questions, so I
Hmm.
found that the audio was very poor.
I will try to not optimize this video and then upload it. Okay.
Right, ma'am. That's then one of the question I saw in the last assignment number seven.
Hmm.
Actually, that got wrong.
Hmm.
Mine assignment actually, out
Okay.
of 10, there was one was wrong.
Okay.
So I was trying to solve through R also and the manually also.
Hmm.
When I was solving manually, I
Hmm.
could not find the answer
Okay.
out of the four options which were given.
Okay.
So, but the nearest one I just checked it, but that went wrong.
Okay. So
That
that
was point
assignment is checked already.
already, yes, ma'am. The marks have been already loaded.
Okay.
And one of the question, that question was, yes, you have gone
Sorry.
through that.
So which was
That's
the question?
question number six, ma'am.
Six. So here it is. So the population of people staying in a society has 100 old, 200 children, 300
Yes.
young people. Considering age as a stratifying variable, a sample of 120 has been drawn from the population using the proportion allocation scheme. The units from each stratum are drawn by SRSWOR. The values are given by this. What are the uh, stratum variance of stratum mean? Okay.
Yes. So the answer has been that 0.0322.
Hmm.
I found it somewhere. Just a moment, ma'am. I just try to solve. Yes, I solved it, but I through R the solution which was uploaded then
Hmm.
in the solution file, that was okay. But when I was trying to, but I could not get my answer was 0.077. It was
Okay. So firstly, it is let me just uh let's
with the
just take a screenshot.
SRSWR method. The variances were the starter variances were 4, 9, 16.
Okay. So I have just taken it here. Now, okay. So firstly, it is a sample is 120 and done with the help of proportional allocation. So it is
Yes,
100, 200, 300. So basically, 600 and
20, 40, 60 are the starters
okay. So it is
by
20, 40, 60. So okay. So these are the one. Okay. So this is 20, 40, and 60. Correct. So 120 and then they are in 2, 4, 6. Okay. Now S1 is square is 4. S is square I'm writing 4, 9 and then 16.
16.
Okay. So what is the variance of stratum mean? So y bar st what is the variance of stratum mean?
Y bar ST.
Okay, so firstly, we need to
100 by
find.
60 it will be. You just solved one example in the last class. Last I think it's last class.
Okay,
A similar question was there.
so variance of y bar st is given by this.
Yes, ma'am. WI is square
Okay,
and I
so
minus something.
okay, so wi is square. So wi is basically
100 by
an
600.
okay. So it will be 100 upon 120.
100 by 120 or maybe maximum 600.
Oh, oh, sorry, 600. Yes, sorry.
100 by 600 square.
Okay, so it is basically 1 by 6 square.
1 by 6 square.
So it is 1 by 6 square, 1 by 3 square, and then 1 by 2 square.
Two
Right?
square.
Okay. Uh, the next is ni minus ni, and
And I
ni.
means 100 minus 20 by 100 into 20. That will be.
Uh,
Or am I wrong? That's 100 minus.
and s1 is square is 4.
Here it will be 4. Yeah.
Then it is 100 minus
40.
40. No, sorry,
100,
200. No,
200 minus 40.
it is
Into 9.
9, and then it is 300
300 minus 60 by 360.
into
20,
60.
16.
Okay. Okay, so if we will try to solve it, it will be 100 minus 20, 80.
80 by 18,000.
80 times 4, and this one is 2000, and then 36, right?
Yes.
Plus it will be so 9, and this 1 by 3 square can cancel out.
Is cancelled.
So
So
it will be 1,
160 by 8,000.
and then here, so
This
it was
4, this
4. I can just write 4,
240 into 4.
18,000, and here 300 minus 60, so it will be 240.
Yes.
Here I can do 2 9, and here I can do 1000, and here 40. So basically it is 4
It
upon 900, and then 3 solar, so 2 by 100, and then plus okay, so this is just 4 times 24, 1800. Okay, so if I will just do this here, so 4 by 900 plus 2 by 100 plus uh
it is 6
4
watt.
times 24 divided by 1800. Yeah, so it is coming at 0.0778.
Yes. This was the answer actually. I was trying through R also.
Hmm.
Answer was same, the 0.077. Whereas the answer in the assignment given and the correct answer which was ticked,
Hmm.
that was 0.03 I could not find that answer, so I wrote a mail then,
Hmm. Okay. And
but I have not received any reply from NPTEL.
okay. So what you can do is that create here uh,
Yes,
QA continue. Do not write the mail. I don't think they write here, and
okay,
start a new conversation. Okay, and in that, why I can't do that? Sorry, it is a problem. Okay, and from here you can just write uh, to this, and then the Prashant sir just gave the reply. I think most of the time. So here you can do. Okay.
right, ma'am.
So even if he will not this reply to this, then I will ask him. Okay.
Right, ma'am. Because only that question's answer went wrong.
Okay.
Remaining all were right.
Okay. Okay, then I'm ending the class if there is no question.
Thank you very much.
Okay.